Hello everyone, my name is Matt Barami from Wolfram Research. Welcome to the third session of our live coding series with Anton Antonov. If you are joining us for the first time, Dr. Antonov is an applied mathematician with more than 20 years of experience in algorithm development, natural language processing, optimization, and machine learning. Today will be the part 3 of live coding series on quantile regression workflow. And Anton is going to look into the certain advanced quantile regression topics. Let us welcome our instructor, Anton Antonov.
Thank you, Matt, and thank you everybody for joining this presentation. So today we're going to talk mostly about two topics. One is about doing simulations based on quantile regression, decomposition of the time series, and how these simulations can be used in operations research. The second topic is applying quantile regression in 2 dimensions and 3 dimensions. We're going to look in related applications and what it can be useful. And for the last topic, if we have time to discuss, I'm going to be discussing how the workflows in quantile regression are organized. So this notebook, it's going to be shared after the presentation on community. There's some links and additional code and data in it. For example, here are the packages which are going to be used. Here are some additional functions which we're going to be using later on in the notebook. So first, we're going to be looking into simulations of time series and the potential applications to operations research. I'm not going to show the actual applications, but I am going to indicate what it is needed and how the simulations are done. Before going further, I would like to mention in this notebook the different sections. The number in front of the sections corresponds to the number of the topic, which is given here in the top section. All right, so this data is from the National Research National Renewable Energy Laboratory. And they have monitored a certain building for for a year. The data is much more with much higher granularity than presented here. I resampled it to be into intervals of 12 hours. I think the data is like half an hour or 1 hour granularity. So what we see here in these plots is that, let me actually try to change this in order to be a little bit more visible. Probably I'm going to remove the magnification. All right, so we can see that they have measured and kept record of the outside temperature, and they have been looking into some variables, like say some inside the building variables, like a kilowatt of electricity spending on heating, on cooling, on lighting, and etc. Let's concentrate, pumps, that's interesting. Let's concentrate on the first four variables here. So the temperature, I mean, obviously, I mean, this is there's somewhere, I assume, in North America. It's like we can see that we have winters, winter kind of weather temperature during the months, the beginning of the year, like say January to April. Then in the summer, the temperatures are somewhat higher. And this can be actually anything, like anywhere, like say Oregon, California or something. And then, at some point they can also get lower. And so we can see with the dry bulb and the wet bulb, they're kind of similar. Dry and wet means that you wrap a cloth around the temperature sensor, and one of the cloths in one of the sensors is dry, the other one is wet. You can see that there's a correlation between the temperature and the heating, and this is something to be expected. So even if you look more closely, like the dips here correspond to peaks here and the other way around. So the other thing we can see, I mean, obviously also when the temperature increases, we actually have then the cooling, the energy spent on cooling increases. Another thing we see, it's like how the lights, we have this dips, ups and downs. As far as I can tell, these dips are probably during the weekend when we just don't have that much electricity consumption when it comes to lightning. Just people are not in the office, I assume. If we look into the finer granularity, we probably will see this kind of dips depending of the day and the night. Here, what I see, I mean, roughly speaking, we're around, say, 52, so I assume it's for the weekends. So similar kind of stuff we can see about the other variables. I'm not going to look into them. But for example, imagine that you want to do certain simulations based on this data in order to produce some kind of energy saving strategy or some other kind of scenario study for this building. And so this is what operations research might be doing. I mean, we're trying to devise a strategy. So we need to have, it's not just the analysis we need to do. We need to outline the strategy. We need to know what actions have to be taken from different scenarios, of the different actions which are possible and not possible. For example, maybe we can decrease the cooling or decrease the heating, but then what is the impact on the people and etc. And so other things like that. So after these scenarios are outlined, then we need to investigate how they're going to pan out in the long term. What are going to be the outcomes? Are going to see some plausible and successful outcomes with these actions according to the different scenarios. So in order to evaluate these strategies, it might be one of the approaches is to generate similar data which adheres to this, but it's random, and kind of see, is it going to work out. Also, if we can simulate the data, we can change some of the parameters here. We're not going into the changing of the parameters, but this should be a sufficient motivation of why we do simulations. So here, this is I'm doing quantile regression on each of the signals which are of interest. As I said, we're going to look into the top 4. So this is the temperatures, the cooling, and the heating. So, and I have you can see I have fitted through them, all of them around like 11 regression quantiles, 11 curves. And now between these curves, I'm going to be doing simulations. This can be explained probably somewhat better if I take this one of these objects, and so I can ask myself what would be the conditional probability. Just a moment. Say certain time, and let me do the time I have in mind. It's going to be, say, we're taking the first object, and I'm going to do it somewhere in July. So this actually, very interestingly, I don't know what are the years, because I haven't seen that in the data. So initially, what I'm going to do is to produce 2000. I strongly suspect it was 2011. And so I'm going to do this. And ideally, I'm going to make them plot. So, okay, something here, I'm simply not familiar with the data points here. So I'm just going to pick a random point from the data which is being plot here. And well, let's assume that this is going to work out. And probably, yeah, well, I need to add the timing. All right. And that, I mean, this what was supposed to demonstrate is that if I use the conditional probabilities, I can actually generate randomly generate new values between these curves here. So knowing how I have fit the signals, I can actually make these random generations. This is going to be done here in this section. So, I mean, this first line here just plots the original signal, right? And we can see because we have fitted the curves. If I didn't do this, this is going to produce both the curves and the data. But I actually want to just see the data in this particular case. Now here I'm going to do simulations. So I'm simulating the signal, and you can see every time I'm running this changes. And what is being produced kind of adheres to what we see here. Well, not completely, right? I mean, it is supposed to be a simulation, so certain randomness is expected. The randomness which is being produced and concluded, it's using the regression curves. It's a unique property, a unique ability you have with quantile regression. So I'm going to concentrate my focus on two variables. Like this is the temperature variable, the first one, and the one for the heating. So we can see they reversely correlate. And so this is my original signal for the heating, and this is my simulated one. So when I do the simulations, we can see here I have specified 365 points. This is because we have 1 year. So I'm basically saying, yeah, simulate this signal for when it is just an integer here, not a set of points. It's going to partition the domain of the curves into equal intervals corresponding to the points. And this is producing the signals. Now, there's a question here, though. Although we have simulated the signals, and they probably, and we can see that they kind of loosely adhere to those. This doesn't mean that the combination between this simulated signal of the heating and the one for the outside temperature, but they are valid combination. Meaning, in certain circumstances, we can imagine that the temperature here is going to be relatively lower than the original one, and here the heating is going to be also like lower, not corresponding to the actual, what is going to happen. So how are we going to prevent this kind of cases? So the problem with this approach is that with the quantile regression simulation, it's not a problem per se, but the quantile regression just gives us the ability to simulate one signal. It's not about the simulation of, say, a combination of 2 or 3 or 4 or 5 or whatever, signals in parallel, like what we have here. So one way to do that is to generate the random points, and then actually eliminate the ones which don't belong to the expected distribution of points. And here it's a very useful feature Mathematica has, a relatively new functionality, learned distribution. And with the learned distribution, you can actually find the anomalies. So this here, I learned the distribution, and the distribution here, it's, you can see here I generated the points from the original data. I took those values. I just plotted the points here. This is the distribution. It's like we see this kind of negative correlation between them, which is to be expected. The idea is that here I'm learning the distribution from the points I have produced here, and I'm producing 320 points. So this 320 points, it's an interesting, I mean, I can use this Lone distribution to produce random points, and this is an alternative of using the quantile regression. The thing is that this produces random variate of the combination of the two values. It doesn't produce time series, so I do need quantile regression to produce the time series. I made this example just to show that we have London distribution, this distribution as any other object. We can use it in some other functions, like say random variate, and do some random points, generate random points, produce new stuff. And now I can use those original points again from the original data to produce a anomaly detection function, which has which has been done in a certain way. You can see what when I run this, I mean, there's some kind of work is happening in the background. All right, so let me do the simulations. So here I have taken the simulations of I'm simulating over the objects I have, and here we can see this. This is the simulated points. This is the first variable and the fourth variable, which is also being used here, the first and the fourth. And let's see how it looks. Here we find some anomalies, and here from the function we generated here, the anomaly detection function we generated here, we can see what are the anomalies. But here I have plotted the new points. Let's actually plot the original points and see how these are obviously outliers according to the original points. If I plot also, let me plot the points which we started with, the points in green. These are the points which came from the simulation. And you can see many of them, they kind of, they're close enough, or they're considered close enough by this anomaly detector. This can be, I can expand on this in a more geometric way to explain how is this happening. One way to do that, and let me see how well this is going to work here, is to actually use geometric nearest neighbors. So basically, for every point here, if I want to figure out which point is an anomaly, I'm just saying, well, a point which has few unknown neighbors according to a certain radius is going to be an anomaly or an outlier. And basically, what I'm going to do is I'm going to scan all points here. When I scan the points, I'm going to find the average radius of the top 12 neighbors, and then use that to make a simple classifier, yes and no, of which this is a point belonging to the distribution or not. If I show what happened here. All right, so if I take this this object, and if I take the context, actually, instead of taking the context, I can just take the nearest neighbors function. I mean, this is what this is. It's a nearest neighbor. This is a nearest neighbors function produced by nearest, which has been founding the radiuses based on the Euclidean distance. And so, yeah, and this is how this outlier detection is working. This is also, I mean, you can see it's somewhat faster than using Mathematica directly, but it has some drawbacks. I mean, I can manipulate some of the, I mean, I can, if I don't increase the threshold factor, if just like say, keep it at 1, I can detect these points as an outliers. And you can see if I try to put the original points here, this actually kind of makes sense. Let me put here another color. The points in red, which are marked as outliers from the new points. They actually don't seem to be that close to the points in blue, which is the original points. I can relax this, if I increase the radius, I mean, you can see more of the, more points are considered to be close enough, and we have fewer outliers, but still, the ones which are found, are pretty good. And at some point, I guess I need to settle and figure out what threshold we are going to use. Something like this, some kind of training like this is happening in the background with Mathematica. They don't necessarily use nearest neighbors. They're probably using some other, distributions for learning. So to summarize what we went through here, we started with certain data which characterizes the operation of a building. We have the outside temperature. We have some variables like heating and cooling. I want to simulate the variables involved in the operation of this building. And so I produced a quantile regression with sufficient number and breakdown of quantiles. Then I do the simulations. I mean, I can do the simulations directly, very easily, through the quantile regression monad. But I'm actually wondering, to what degree the combinations of the simulated signals are going to be valid, are going to be something that is expected. Because of this, I learned the distribution, and I use this learned distribution to make a anomaly detector. I mean, this is happening in the background here. This anomaly detector is going to filter out and mark unlegitimate combinations of simulated values as outliers or anomalies, and that's why I wouldn't be using it when I do my operations research investigations. There's an alternative way to do that, and this is by doing nearest neighbors. All right, so we're going to move to the second topic of this session, which is let me just condense some of the sections here. Which is
question, Anton.
Yeah.
Sometimes you use the term anomaly, sometimes you use the term outlier. Is there any difference between the two?
Very good question. Outliers are point-wise anomalies. Anomalies can be both outliers, but also they can be a sequence or a sequence of values. Also, anomalies sometimes, as we saw that in the previous lecture session, structural breaks, they're not necessarily outliers, but they do break the signal in such a way that if you do linear regression, you get two separate lines. So anomalies is more inclusive. It's a wider term. Outliers, in the way I see it, in the way I use it in this monad at least, they're much more point-wise type of objects. I use anomalies also because it is used as a terminology, as you can see in the Mathematica functions, like anomaly detection and etc. In some of the examples we also saw, we partitioned the signal into different parts, like say overlapping partitions of 4 and etc. And we found the anomalies. But yes, we are finding anomaly. This actually illustrates the point. We found this sequences of 4 elements to be the anomaly, not one of them to be the anomaly. So I hope I answered your question.
Oh, yes.
All right. So we're going to the second topic here of how to apply quantile regression in 2D and 3D, in 2 dimensions and 3 dimensions. I have generated some data here. And so you can see, let me plot the 3-dimensional data. All right, so we're basically having data like this. And so here you can see that this is not, I mean, it has very little to do with what, say, time series signals have. Maybe if I partition this picture into 2, right? I can apply, quantile regression on each of these separately, but still, it's not a faithful way of applying quantile regression. And the other is that similarly in 3 dimensions, you can see that, for example, in this, how we have this ellipsoid and the points are concentrated around the surface of the ellipsoid and on the poles, right? The North Pole and the second pole. It's this here, it's more like concentric kind of spheres of of points. So yeah, how we are going to be, how we can apply quantile regression to this. One way to do that is, I'm going to show that here, hopefully relatively easily. So this is a function. This function is experimental. The quantile envelope experimental in my package. I developed it a few years ago. I haven't went much further than that, but decided that it's working good enough. So I'm going to demonstrate how it works. And also now Mathematica with learned distribution and some of the other functions. It's probably less important to have this. So you can see here, I decreased the number of directions. I'm going to explain what directions mean. So if I have the original set of points here, I can find the center point, the center of mass. And in this center point, find out for the distance, of say, which a line which separates the points, like say, 70% or 80% above and 20% below. And so this is what is happening. You can see this actually in the lines here. So I have used, this is at 70% probability, 70%. So basically this is what this line is. Now, we hope that if we increase the number of lines, we are going to have better and better approximations of what's going on. And that's true. We need to be, this is not all. We need to be careful how we do the intersections and how we do the envelopes. But it is a way to do this quantile regression, and it does have the properties of the same properties of the using quantiles. And so it does separate the signal according to certain set of probabilities. This here, it's also, let me actually show this. So if I do this, you can see that there are actually some points inside. So if I tighten this, if I make a tighter line, I mean, you can see that I can say that the point which is here, this one here, it's actually an outlier, because all of the other points, they actually don't belong so closely to the center of mass. So, I mean, using this kind of envelopes, we actually can find outliers, points which are outside of points which are like too much inside, and etc. So this is, I'm not going to talk too much about this, but so here, one interesting remark is that we can actually do, this can be done also with the region functions. Let me see. Can I do this? So, well, Mathematica has the so-called region functions, like, and they're very helpful to do stuff. When I initially implemented the two-dimensional envelopes, the region functions didn't exist, but then for the three-dimensional implementation, this actually, they were already in place. So it was actually relatively easily for me to implement three-dimensional quantile regression. The three-dimensional quantile regression does exactly the same as the two-dimensional one. We're taking the original set of points and we're just rotating it in different directions. We're finding the center of mass, we're rotating it in different directions, and instead of a line, of course, we're putting a plane. And this plane separates the points according to certain probabilities. And so here I probably used too aggressively, too large, the number of directions was too large. And actually, let me just stop that too and make only 10. And so, yeah, I mean, it is very chopped, but, it is actually, it demonstrates what exactly has been, how exactly this algorithm is working. All right, so, all right, great, whatever. What is the application of this? It's just, making this kind of nice pictures and analyzing the signal. So here I'm going to actually discuss another topic, which is, how we going to find outliers in a certain set of points. And so Here I'm going to be using a particular data set, which I took from the University of California, Irvine. And this data set, you can see, it's not that important what it is, but I'll explain nevertheless. So this is invoice data, fairly big set, around 65,000, 66,000 records. And it's basically, we have different invoices, and in each invoice we have different purchases, different items with different quantities, different unit prices, and etc. The interpretation here is not that important. What I want to do is to actually consider, let me see, is this going to produce what I expected? All right, yeah. So we have only 2 numerical columns. And because of this, I'm going to add a third column. Let's call it a discount column. And in this third column, I'm going to, let me again, in this test data, find the summary. And now I'm kind of asking myself, is it possible to find outliers in this 3-dimensional data? Actually, this histogram, it's not particularly, we need to do something else here. So I'm going to find the logarithm of the data. And yeah, okay, so we can see that there's certain structure here, right, after we find the logarithm. And so in general, when we do this kind of stuff, it is a good idea to standardize the data. So this is what I'm going to do. The next thing I'm going to do is standardize the data. And if I standardize the data, if I find the summary, we can see that I'm having, it's much tamer, right? The ranges are much different, better. And so let's actually plot the standardized data and the logarithm of the standardized data. So yeah, this it's quite a lot of points, and this is completely not what I expected. So let me see here. Well, one of the problems we have is that the data being standardized in this way, it's actually when we take logarithms, it's not going to produce. We need to offset it. So this is what I'm doing here. So I'm going to standardize it, going to do certain offsets, and in order to produce only positive values. And now this plot should look decisively better. All right, yeah. So this illustrates why we should logarithm the second one, because it corresponds to the logarithm 10. Because here we see that there's some points which are out, but we don't see much of the structure. But now we see better what is going on. So this here, and this is where the application of the 3-dimensional quantile regression comes into play. I'm going to sample this standardized data, and I'm going to make an envelope, right? And so basically everything outside of this envelope is an outlier. And you can see I have used, I used 99.7%, right? And 10 directions. Maybe if I feel brave, let me increase the number of directions. This can be, but also the sample of points is different. Actually, let me repeat this experiment with putting seed random, like to be some value in order to reproduce the result. And so, yeah, this is with 20 elements. Let's see if it is with 10. It's going to be different. Somewhat different. All right. So, of course, this is just a sample. So what I'm going to do, I'm going to actually apply it over the whole set. So far, I have convinced myself that this is more or less working. And you can see I use this quantile envelope region, which I was demonstrating earlier. And now after we have done this, Mathematica has this nice function that from a region, you can produce region member function. So let me show it here. And you can, I mean, certain formula and etc. But you can form different predicates about which points belong to this region and which don't. So if I do that, and so this can take like say around 15 seconds. And yeah, well, this is computing. I'm going to. I want to see also in this tally what is going on. So we see that of this 65.5 for 65,500 points, 1,000 points are considered to be outliers. This might be a little bit too many. And so what I'm going to do here, I'm going to change this. I'm going to add this. I'm going to tighten up this function, the threshold, the probability threshold. I'm going to recompute this again, and this is going to produce presumably, at least half a less number of points. And while we're waiting for this, I'm going to, well, nearly 10 times less outliers. And let's now plot the outliers. And so yeah, we can see what these are the outliers. We found with this using this approach. If I use my original threshold, and again we're going to wait and to do. Yeah, let's see what is going to happen. I mean, these points, they should be much more points being marked here as outliers when the computation finishes. Yeah, and as expected. This also provides, this here, we found both top and bottom outliers. Although in 3 dimensions, what is top and what is bottom, it's a little bit, but I mean, this should be also enough to, if we want, say, just top outliers and bottom outliers, we can actually easily modify the thresholds here and produce those results. Well, this is the second topic, and I think we have very little time to discuss the third topic. Mats, do you think I should proceed with the third topic?
Let's see. I guess, if you don't mind, we could wrap up our session for today, and the third topic, we could discuss it, in much more detail for the next time.
Yes, sounds good.
Excellent. Let me check. So, yeah, there is no more question. So thank you, Anton. Let us wrap up our session for today. You were watching the third live coding session with Dr. Anton Antonov. You can watch the recorded video on Wolfram YouTube channel. You can also interact directly with Anton through Wolfram community. Thanks for watching and have a good one.
Yeah, thank you. Bye.